Problem set number 16.10a. Figure 6.39 shows the phase diagram for two partially miscible liquids, which can be taken to be that for water A and 2-methyl-1-propanol B. Describe what would be observed when a mixture of composition XB equals 0.8 is heated at each stage, giving the number, composition, and relative amounts of the phases present. We are given with a mixture composed of two liquids, namely water and 2-methyl-1-propanol. They are partially miscible, which means that they do not mix in all proportions at all temperatures. The mixture is composed of 80% 2-methyl-1-propanol, thus it is composed of 20% of water. The required are the number of phases, the composition of each component in each phase, and the relative amount of the phases. We're also going to describe what happens to the mixture as temperature rises. To properly describe what happens to the compositions and the phases of our mixture as it is heated, we will have three temperatures that we are going to observe. These will be T1, T2, and T3. In this liquid-liquid phase diagram, the area bounded by the curve and the x-axis is where we'll find a two-phase system in equilibrium, and the rest of the area is where we'll find a single phase system. This is where the two components are completely miscible with each other. The highest point of the curve is the upper critical solution temperature, which is the highest temperature at which phase separation occurs. So above that, the two components are fully miscible. So let's go to our solutions. Let's start with T3. This is the lowest temperature of the phase diagram, and at XB equals 0.8, we can see that the point is inside the curve, so it has two phases in equilibrium. Then the water-rich phase, the left part, is composed of about 0.05 moles of methylpropanol per mole mixture, while the other phase, the one rich with methylpropanol, is composed of about 0.87 of such species. To determine the proportion of each phase, we use the lever rule, which is given by the moles of phase A over the moles of phase B, equal to the difference between the mole fraction of methylpropanol in phase B to the mole fraction of methylpropanol in the whole mixture, over the difference between the mole fraction of methylpropanol in the whole mixture minus the mole fraction of methylpropanol in phase A. Substituting values, we will know that the methylpropanol rich phase B is about 10.7 times more than the water-rich phase A in this temperature. Raising the temperature to T2 would still create a two-phase equilibrium since the point is inside the curve, so the methylpropanol increased its mole fraction in the water-rich phase to 0.2 from 0.05, while its composition in the other phase decreased to 0.85 from 0.87, which wasn't that significant. Again, we use the lever rule with the same formula, and we will now see that at a higher temperature, the methylpropanol rich phase is now 12 times more than the water-rich phase. Raising further, the temperature to T1 would intersect with a curve, which means that it is now a single-phase system. This is composed of 0.8 moles methyl-propanol per mole mixture, and since this is a single phase system, then automatically the composition of water is 0.2 moles water per mole mixture. Using the lever rule in this situation would be impractical since the system is now only composed of one phase, so we wouldn't need to compare the proportions of two phases. Thus, if we increase the temperature further, the system would produce a single phase liquid-liquid equilibrium. Arigatou gozaimasu.